High-speed video recording systems allow us to observe the momentary or first phenomena in real world. Precise analysis of 3D deformation of human body is essential in athletics and biomechanics. Collision analysis commonly carried out in car industries to assess the safety of the vehicles. To understand the deformation of shape in 3D, high-speed shape acquisition is required. Our system is composed of a high-speed camera and an off-the-shelf DLP projector. The projector illuminates the scene, and the camera captures the images. The key component in our system is the DLP projector. Let's see the inside of the projector. Unlike liquid crystal display systems, DLP projector generates the frames by reflecting the incident light rays by the mirror on an optical semiconductor. This component, Digital Micromirror Array Device or DMD, contains a rectangular array of up to 2 million microscopic mirrors. Each mirror on the DMD can switch between two orientations. Incident light is reflected by the mirror towards either the outside screen or onto a black surface within the projector. The mirror can switch in a few microseconds, enabling high-precision control of illumination. We call this way of light modulation as temporal dithering of illumination. The temporal dithering pattern of a projector differs among different projectors. Suppose we project a 16 by 16 grid of 8-bit gray values onto a white screen by a DLP projector. It looks a static grid image to human eyes, but if the projected pattern is observed using a high-speed camera at 3000 Hz, we can see the change of intensity. By collecting the intensities observed at the same pixel, the table of temporal dithering function can be created. Once the table is obtained, the intensity input to the projector can be identified from the intensity observed by the camera. In our acquisition system, we use the color stripe image as the illumination pattern. The stripes are composed of 512 distinct colors, such that the minimum distance between the dithering patterns is maximum. Only a single image is projected to the scene by a DLP projector. Since we use a single image as an input to a projector, the illuminated scene looks static to low-speed cameras such as human eyes, but when we capture the scene at 3000 Hz, the temporal dithering of the illumination becomes visible. We put a planar surface into the scene at known distance. The depth map of the scene can be reconstructed by finding the best match between the stripes on the object and the planar surface. Now we show the estimated correspondence of the stripes. The depth map can be recovered by the triangulation between camera and projector. The recovered 3D shape of a static statue is rendered from multiple viewpoints. This example shows the 3D acquisition of a moving hand. The object moves too fast that the object is blurred in 60 Hz video. In the high-speed video at 3000 Hz, we can assume that the motion is negligible within adjacent frames, while the illumination differs among the frames. This video shows the 3D deformation of the hand. The slow-motion video of the deformation can be easily generated because we have 3000 depth frames per second. Now we show the rendering from a side view. Next, we show the result of applying our technique to pen spinning motion. We used 25 successive frames in high-speed video acquired at 3000 Hz to reconstruct one depth map. The 3D deformation of the shape is rendered at real-time speed and slowed down to the quarter of real-time speed. Now we show the rendering from a side view. Next, we show the result of applying our technique to a piece of paper waving drastically. We can generate 3000 depth maps per second by sliding the window of the 25 frames along time. Now we show the result of applying our technique to face expression. In summary, we have presented the high-speed system of acquiring 3D shapes. Our system is composed of the optical components that are easy to obtain and can capture the scene at more than 1000 frames per second.